fundamental counting principle. Today's focus is that, and when do we use it, and how do we use it? Okay, so let's first start with investigation. Suppose you roll a standard red die and a standard blue die. So we have a red one and a blue one. Okay, so we have a blue, and how many, if it's a standard die, what are the numbers on a standard die? 1 through 6. Okay, and we're going to roll also a red die. Okay, and it says describe the sample space for this experiment by listing all the different possible outcomes. So by making this chart is one way we can make all the outcomes. So for example, I could roll, I'll put the blue first. So a blue one, and a red one. A blue one and a red 2. Do you see how these line up? A blue 1 and a red 3. A blue 1 and a red 4, 5, and 6. So that's one set of combinations. And by making this chart, I can come up with all the combinations. So the next, what would this be? 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. I'm not going to put all the colors in right now. And then next would be, so fill in the rest of the chart. And 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. Question, is 3, 3, is that, remember the colors are different, right? So one's going to be blue, one's going to be red. And you only see it twice, or once, because 4, 1, 4, 2, 4, 3, 4, 4, 5, 6. And last. So how many total combinations do we have here? 36. There's 36 total combinations. Was there an easier way to figure this out? How do you think there was 36? Yeah, what's the easier way, Levi? 6 times 6. If we have our red die and we have our blue die, how many choices of numbers do we have for the red? We have 6 of them, 1 through 6. How many choices do we have for the blue? We have 6 of them, so 6 times 6 is 36. This is the fundamental counting principle. So we could make charts. We can also make trees. I'll show you how to make a tree today as well to figure out all the combinations. But the fundamental counting principle, as long as they are mutually exclusive, and we're going to learn about what that word means, we can use them, means they're disjoint, they're not related, and we want this and that. So they're related with the and word. Okay, so we want a blue die and a red die, and we're rolling them both. Okay, then we could just multiply them, and that's the fundamental counting principle. So looking on the next page, I'm just going to do some highlighting. You can maybe underline or highlight. The fundamental counting principle, it's really important to know that it's related to when you see the word and. Okay, so it's used when we see the word and. You cannot use it if it's or. If I want to do this or that, okay, then that's a different situation. And when we have and, we're going to use multiplication. And always applies multiplication. Okay, multiplication. Or is going to imply addition. The fundamental counting principle states that if one task can be performed in A ways and another task can be performed in B ways, then both tasks can be performed in A times B ways. And that is the fundamental counting principle, what we just did. So there are 6 ways we can roll the blue die, and there is 6 ways we can roll the red die. So if we're going to roll both red and blue, it'd be 6 times 6. So important things to remember about the fundamental counting principle. Fundamental counting principle can be extended to more than 2 tasks. So we could have 3 or 4. So if there's another task, so there are A ways for the first, B ways for the second, C ways for the third, it would be A times B times C. So we can extend it more than just 2 things. The fundamental counting principle does not apply when tasks are related with the word or. Okay? In that case, in an or situation, in the case of an or situation, so or implies, well, let's talk. There's 2 situations, okay, with or. If they say the word or is always addition. And is going to be multiplication in this unit always when we're finding out the number of possible combinations. So there's 2 situations with or. They're either going to be mutually exclusive or not mutually exclusive. What does it mean to be mutually exclusive? That's a very important term. Okay, you really want to know this. So if tasks are mutually exclusive, okay, they are disjoint sets. So A and B are disjoint. So if it's A or B and they're disjoint, then the number in A or B, remember union is or, and it's addition. Okay, and in the event that they are mutually exclusive, they're disjoint, it's just the number in A plus the number in B. There is no overlap, so we don't have to worry about the overlap. Make sense? So these are number of vegetables, and this is number of fruit. I couldn't think of the word fruit. Okay, if I want a vegetable or a fruit, be the number of vegetables plus the number of fruit are my options. Okay, if it's an or situation. If they are not mutually exclusive, so what does that imply if they're not mutually exclusive? They're not disjoint. What do they look like? What is there? See what's happening with them? If they're not exclusive from each other, they're inclusive, I guess. There is an overlap. Okay, there's going to be an overlap. So they're not disjoint. So the word mutually exclusive implies disjoint, not mutually exclusive, they're not disjoint. So if I, again, have an or situation, so all of this, these are for or. Okay, and so or you could either be mutually exclusive or not mutually exclusive. And so because of this overlap, the number in C or, remember this is union, so or, union, the number in C or D would be the number in C, the total number in C, plus the total number in D, and then minus the overlap, because we've added that twice. C and D, right? Remember this middle part is C and D. Okay? The principle of inclusion and exclusion must be used to avoid counting elements in the intersection of the 2 sets more than once. So we have to use this principle to make sure we don't count something twice. Outcome tables, organized lists, and tree diagrams can be used. So is there one on the next page? Yeah, so let's look at the next page. And I'll show you how you could do that. So we could also use a list. Hannah plays on her school soccer team. The soccer uniform has 3 different sweaters, red, white, black, and 3 different shorts. So red, white, black. Now in this situation, is it an and situation or an or? Ignoring this word here even. Think about it. When you pick your outfit, are you picking a sweater and a short, or a sweater or a short? And I sure hope so. You're going pantless, maybe. Okay, and that's not pretty. So it's an and situation. So this is a situation where we can use the fundamental counting principle. Okay, so there's our sweaters and our shorts. So I'm going to show you 2 ways. One is with instead of a chart, I'm going to show you with a tree. How many sweaters do we have to choose from? How many sweaters? 1, 2, 3. Okay. So the colors are red, white, black. Okay. And after we choose our sweater, how many shorts do we have to choose from? 3. We could have a red short, a white short, or a black short. Red, white, black, red, white, black. So our total outcomes, I could have red and red, right? Red sweater, red shorts, red sweater, white shorts, red sweater, black shorts. We can have white sweater, red shorts, white sweater, white shorts, white sweater, black shorts, and then black sweater, red shorts, black sweater, white shorts, black sweater, black shorts. So total of how many combinations? How many is that? 9 combinations. So trees are fine, charts are fine. Are they more work? Yes. Could we have used the fundamental counting principle? Yes. So how many choices for sweaters did we have? You said we had 3 times the number of choices for shorts is 3, so 9 combinations. A lot easier using fundamental counting principle. It's going to save time. Lots of time. Drawing that out, it's doable. You can literally write out all your combinations. Now this is just only 2 situations with 3 options each. Could you imagine like 4 situations with like 10 options each? That's a big chart. No, thank you. Okay, so a luggage lock opens with the correct 3-digit code. Each wheel rotates through the digits 0 through 9. Okay, how many digits is that? The 0 through 9. Total of how many digits? 10 digits, right? If it's 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or not 10, 9. It gives you 10 different digits. The total of 10 different digits are your options. So 10 options for each wheel that you're rotating, okay? How many 3-digit codes? So when we set up the fundamental counting principle, we have 1, 2, 3 different codes, or 3 different slots, right? Your little luggage thing has you're rotating. So the first one, how many choices do we have? How many digits can we put in the first slot? 10. How many digits for the second? 10. So there's no restrictions right now. In the future, we're going to put restrictions. I'm going to say things like no repeats or stuff like that. And then the last one's still 10. So a total of how many combinations can we make? That would be 1,000 combinations. Different combinations you can make for your little codes on your luggage. Now, same problem. Suppose each digit can only be used once. So that's in a situation where we want no repeats. How does that change the problem? Well, we start with the very first slot. How many options do I have for the first one? How many digits can you put there? 10. Now, you've used a digit. How many options are left for the second? 9. Because you've used one of them, now you have only 9 because we want no repeats. And now how many options do we have for the last? 8. And 9 times 8 is 72 times 10, 720 different combinations. We want no repeats. Okay, we don't want to use 0, 0, 0. I think that's how they come, right? I don't know. I haven't bought a little luggage thing. Okay, next page. Are you familiar with cards? Okay, well, these are clubs, diamonds, hearts, spades, Oh, what? Oh, yeah. I did this last time. Okay, when you play a game and you choose a suit, you always go alphabetically, right? So it's habit for me to go play a lot of cards growing up. Clubs, diamonds, hearts, spades. Sorry, clubs, spades, hearts, and diamonds. Okay. Our face cards, which ones are your face cards? Yeah, just the Jack, Queen, King are face. All of these are face cards. And yeah, just those are face. I don't know. These are black. You can't really see that on yours, so you might want to write that in. Black. These are all red. Because yours is not in color, sorry. Okay. So count the number of possibilities of drawing a single card. So you're only drawing one card. Okay? Drawing only one card. You're getting either a black race card or race card. That sounds weird. It's supposed to say face card. It's an unfortunate typo. Right, right? That's okay. Black face card or an ace. So this is an or situation. We're only drawing one card. So we're not using the fundamental counting principle here. Right? If I was drawing two cards, then maybe a different situation. But right now we're just drawing one, and it's an or. Now, so this is our A, and this is our B. Now, if we want the number of possibilities for A or B, the question is, are these disjoint sets? Can you have an ace that's also a black face card? No. So they are disjoint. They're disjoint. So it's just going to be the number of black face cards plus the number of aces. So how many black face cards are there? How many? 1, 2, 3, 4, 5, 6. How many aces are there? 4. So we have a total of 10 different possibilities. So face cards are just Jack, Queen, King. So there's an ace is not a face card because there's no face on it. Yeah. Okay, so either a red card or a 10. Now, are these mutually exclusive? Are they disjoint? Nope. So not disjoint. Notice we're using or. So the number in A or B equals the number of red cards plus the number of 10s minus the number of red 10s, A and B. The intersection, number of red 10s. And if it makes more sense, you could actually even apply the numbers, like the number of red or 10 equals the number of red plus the number of 10s minus the number of red and 10. If you want to, instead of use A and B. Okay, so how many red cards are there in a deck? There's 13 in each suit, and how many suits are red? 2, so there's a total of 26 red. How many 10s are there? 4 minus how many red 10s are there? The overlap, how many red 10s? 2. Okay, 26 plus 4 minus 2, 28 different cards. Number of possibilities. So next unit, probability, we're going to take it one step. We just ask what's the probability of picking. So it'd be 28 out of total of 52 cards, right? That would be the probability. Your number of combinations over the total options. We're almost done. We're right at the end of today's lesson. Not so bad, is it? An Alberta license plate has 3 letters followed by 3 digits. Okay? For example, ABC 1, 2, 3. The letters I and O are not used to avoid confusion with the digits 1 and 0. Okay, so we're setting this up. If I'm going to use fundamental counting principle, there's 6 different slots, right? The first 3 are going to be letters. The last 3 are digits. Letter, 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 digit, digit, digit. Now, because we're not using I and O, how many letters do I have to choose from to put in the first spot? Well, how many are in the alphabet? You should know this. That's something you'll have to know for you might have to sit there and count A through Z otherwise. There's 26 letters in the alphabet, okay? If you don't know that, put that on your study sheet and know it. Otherwise, you'll be counting letters A through Z. Alphabet? No, A, right? That's embarrassing. I can't spell. Okay, anyways. All right, so if we can't use I and O, how many choices do we have? How many choices do we have? 24. We can't use I and O. So the first slot, 24 for the first letter. Can we repeat letters? Yes, so the next one would be 24, 24. How many digits? You have 0 through 9. How many digits is that? 10 times 10 times 10. This is where you need a calculator. So 24 times 24 times 24, 24 cubed, times 10 times 10 times 10. Yeah, it's a very big number. 13,824,000. Lots of options. Combinations. They're all the number of combinations. Okay? That's a lot of combinations. But what have they started doing recently? They started adding a 4th number. Have you noticed that on some of the license plates? So why did they do that? Well, it's a growing number of vehicles because people don't have just one vehicle, right? So it's not always just equal to the number. You have to think about the number of vehicles with license plates. So because the growing number of vehicles, the province is changing to plates with the letters followed by 4 digits. So now we have letter, 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 digit, 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 digit. How many more license plates are possible? 1 more 0. You're correct. Because we're adding another, well, another times 10. Yeah. So that would be 138,240,000 combinations. So how many more is that? How do I get how many more? Subtract from how many we had before. So minus the 13,824,000 gives us, I don't know why I use it, it's just a straight line, a total of, I'm just going to help you out here, 124,416,000 more combinations. Just by adding one extra number. So what you'll see in your homework today is you're going to see problems that you have to really watch for the and situation. Are we dealing with, like, if I'm making a pizza and first you have crust type, and then you're going to choose the veggies, and then you're choosing the meat, and then you're choosing the type of pizza. That's a fundamental counting principle because they're this and this and this and this, right? You're going to get more than just one thing. If it's or, that's when you're not using a fundamental counting principle. That's where you have to figure out if it's mutually exclusive or not and use addition. So your homework, if you grab your workbook, it's all of 2.1, which is on page what? Somebody help me. There's 2 pages of work, 26 and 27. That sound right?
Mm-hmm.
So it starts at 26. So page 26 to 27, and that's numbers 1 through 9. Yeah, 1 through 9. Okay. So, yeah.